Okay, good afternoon. I'm Sasha Gerber. I'm from physics, and I'll try in half an hour to make a crash introduction into what we are talking about. 25, yeah. So it will be even crasher than I expect it to be. No, it doesn't work. Okay, thank you for these pictures. I mean, we all use the same pictures when we talk about spintronics or introduction to spintronics. But let's say there is a mainstream spintronics. And mainstream spintronics is based on this experimental plot. And this is the plot of giant magnetoresistance, the phenomena that was the origin of the entire field and gave the Nobel Prizes, et cetera, et cetera. And the idea of giant magnetoresistance is more or less the following. I mean, if we have a heterogeneous system, ferromagnet, non-ferromagnet, and once again ferromagnet, the conductance along this heterogeneous system depends on relative orientation of magnetic moments in ferromagnetic layers. And the idea is that if magnetization is parallel, so spins within each layer are polarized and then can easily transfer from the original layer to the second one and keep moving. If the magnetization is anti-parallel, then polarized spin has difficulties in penetrating the layer which is magnetized in the opposite direction, like here probably, yeah, well. And that's why the resistance is large. So that's why, I mean, if we have this system which at zero field, the arrangement of magnetic moments is anti-parallel, we have high resistance. If we apply magnetic field and we align magnetic moment in the entire system, then we have low resistance, and transition from high resistance to low resistance is what is the origin of the term giant magnetoresistance. Now, it has been discovered when the spacer between ferromagnets was metallic, but in fact the same physics works also when we put insulator between two layers, and then we have tunneling magnetoresistance, but the physics more or less remains the same. The transition of polarized spins from this area to this area depends on relative magnetization of one to the second. Okay. Now, it was discovered at 86, more or less at the same time when high temperature superconductivity has been discovered. Nobel Prize came significantly later, but applications of this came almost immediately, and that's why today almost any computer, all computers today use sensors, magnetic sensors, to read hard disks that use giant magnetoresistance phenomena or tunneling magnetoresistance phenomena. Now, another thing that I will come later a little bit is how to use this tunneling magnetoresistance to magnetic random access memory. This is, again, this is in process, and very likely that within a couple of years we'll have a product that will use random access memory based, which will be non-volatile and based on magnetic materials only. Now, we are talking mainly about some other phenomena which again depends on spin of the electrons, and this is the so-called extraordinary or anomalous Hall effect. Now, the effect is known since 1880 because Hall himself found the phenomena, the effect when he measured foils of iron. And the idea of effect is well, at least phenomenologically, seems to be quite simple. I mean, what you see here, this is, let's say, the idea of the ordinary Hall effect. The ordinary Hall effect means that we have a film, we push the current along the film, we applied magnetic field perpendicular to the film, and then there is Lorentz force, and it diverts the trajectories of all the electrons, never mind either the spin is up or spin is down. But if we have the material, which, for example, which is magnetic, and we have spins up and we have spins down, and we have different number of, let's say, effective number of conducting spins up and spins down, we have an additional effect, and this is the so-called extraordinary or anomalous Hall effect, and it comes from scattering of electrons, which includes spin-orbit interaction. And if we have spin-orbit interaction, then spins up will go one direction, spins down will go the opposite direction, and if their number is different, we have accumulation of charge on one side versus the charge on the other side, and this is the basics of, let's say, extraordinary Hall effect. Now, if we still have spin-orbit interaction, but zero magnetization like in normal metals, we again still have spin-orbit scattering. Spins up go one direction, spins down opposite direction, but since their number is equal, we have no electrical charge separation, we have no electrical field in direction perpendicular to the current, but we have a pure, what is called today, spin Hall effect. Okay, but I shall talk about this one, I mean this anomalous or extraordinary Hall effect. And so we take ferromagnetic field and we push the current and we measure electrical field perpendicular to the current, and it will have two contributions. One of them is the just ordinary Lorentz force, ordinary Hall effect, and this one is the spin-dependent, spin-orbit scattering-dependent extraordinary Hall effect, and this one depends on, in fact, on magnetization of material, magnetic moment of material. And that means that when we measure Hall voltage in ferromagnetic film, we have a signal which is directly proportional to magnetization of material. And that means that we have, in fact, magnetic electric replica of magnetization. So in many cases, I mean, in cases that we are interested in, this contribution is much larger than the ordinary Hall effect, and that's why we directly measure magnetization of material by measuring Hall effect. And that's why if we have, for example, some material without hysteresis, so this curve is just proportional to magnetization of material. And if our material has magnetic hysteresis, we'll get something like that. This is just as we visualize ferromagnetic hysteresis. Now, why is it interesting despite being known for so many years? Well, first of all, we don't understand the effect. I mean, by saying we, probably I should say I, which would be more correct, yeah, because some people claim that they do understand. I don't understand. I don't understand a lot in this phenomenon, and some of these things I shall refer in the future. But even without understanding it, it can be used as a very, very simple experimental tool. For example, when we want to measure very thin magnetic films. I mean, typically the standard methods of measurement, magnetization measurement, means that you have your material, you put it into some kind of magnetometer, and you measure magnetic response. Now, thin films typically sits on some substrate. Substrate has its own magnetic contribution. And if we have a very little amount of magnetic material, this magnetic moment that we are looking for can be negligible to pseudo non-magnetic substrate, but because magnetic substrate is very large. And that's why our sensitivity to magnetization for very thin films is below the sensitivity of squids of whatever we have today. But if our material is still conducting, so all the magnetic response comes through conduction, through signal generated within the material itself. We do not measure the substrate. And that's why it appears to be remarkably sensitive to measure all the possible things in very thin magnetic films, hysteresis, relaxation, whatever. Okay. Now, if the film is non-conducting, if we talk about, let's say, finite clusters of the material, still we can put them within a conducting non-magnetic metal. And then again we have the current, and we have ferromagnetic clusters that scatter the electrons, and we get Hall effect coming from nanoscale ferromagnetic clusters. So this is the case, for instance, you have cobalt clusters, 3 nanometer size, within platinum, silver, palladium matrix, and we measure what we see is just magnetic response of individual nanoscale magnetic clusters. Okay? So this is in fact the thing that we have not finished, and this I still plan to do as a sport, but we want to measure one single ferromagnetic cluster. And this is definitely possible, just the question of making proper lithography. Another thing which is came quite surprisingly, quite recently, is that it appears, well, there is one, well, many problems, but one of very typical materials or devices or systems that are used in magnetism and spintronics are multilayers. And one of very famous type of multilayers is, for example, cobalt palladium or cobalt platinum. Why? Because this is the material with perpendicular anisotropy. Okay, and this is used today for magnetic memory. It's okay. Now the question is why there is a perpendicular anisotropy in this type of system. Okay, so there are two approaches. One of them says, okay, we have a clean interface, sharp interface between cobalt and palladium, for instance, and sharp interface means that cobalt atoms are just on the edge, and this transition break of symmetry introduces perpendicular anisotropy. Another approach says, well, you know, cobalt palladium alloys have very high magnetostriction. And if you have a very thin film with very high magnetostriction and you put it on some non-magnetic layer, you generate a strain. And that's why what happens, I mean, in order to reduce this strain, magnetization should step perpendicular. Okay? Now, if you use ordinary tools, for example, microscopy, X-ray, whatever, and you try to really realize what happens at the interface, this is a very, very tricky business. But it appears that if we just measure Hall effect, it appears one of the things that we do not understand, but is a fact. Hall effect changed its extraordinary Hall, changed its polarity somewhere about when concentration of palladium exceeds something about 75%. This is exactly more or less the range where all the materials with perpendicular anisotropy, multilayers with perpendicular anisotropy exist. So by measuring the polarity of the extraordinary Hall effect, we can know what is the state of the interface. Moreover, one of the conclusions is that in fact when we talk about multilayers, in fact they are not multilayers. They are, let's say, they are alloys with gradually varying concentration, but they are not alloys. And that's why probably in this case we should not talk at all about let's say sharp interfaces between cobalt and palladium, platinum, or ferrum platinum, etc., etc., etc. Okay. Now, another thing which is interesting, this is direction of applications. And when we talk about applications, we talk about more or less three things. One of them is that we are able probably to generate very sensitive magnetic field sensors with sensitivity, and I will talk about a little bit later on, which sensitivity which is at least or by a few orders higher than the sensitivity of the best semiconductors. We can talk about generation of non-volatile magnetic memory that works on the extraordinary Hall effect, and we also, there is a very interesting subject that you started to talk about, and this is merging of spintronics with semiconductors. Now, regarding the sensors, why sensors? Well, to make it, let's say, all this linearity, and it is a very linear. One of, for example, great disadvantages of semiconducting Hall effect sensors is their sensitivity to temperature. I mean, conductance and Hall effect and the number of carriers in semiconductor depends strongly on temperature. Here, we are able to tailor the material in such a way that the slope will not be dependent on temperature. But this is very small, this is fine, low power dissipation because high resistivity, but probably the most important is the sensitivity. You see, this blue line, this is the highest. Now, sensitivity, the definition of sensitivity here, this is just the slope in, let's say, ohms in Tesla. So what is the change in the measured ohm when we change the applied magnetic field? So in units of ohms per Tesla, the highest sensitivity that we know today in the best semiconductors is of the order of 1,001 kilo ohm per Tesla. Now, this number has already been passed, so there were reports of, let's say, about 10,000 ohm per Tesla, and this number, this is not yet published, but recently we got sensitivity in the range of, well, almost 1 million ohm per Tesla, which is about 3 orders of magnitude higher than what has been achieved in semiconducting sensors. Now, sensor is good when our magnetic response does not have hysteresis. But if we have a material with perpendicular anisotropy, for instance, and we have hysteresis, then these materials can be used for memory. Now, what people do today in order to increase the memory capability, there are 2 ways. One of them is to make each memory unit smaller and smaller and smaller. Okay? And that means, for instance, by being patterned media for hard disk. Now, if you want to get the, let's say, 1 terabit per square inch, that means that each memory unit has to be smaller than 20 nanometer size, and this has 2 problems. One of them is just to do it properly and on a large wafer. The second one is that when the memory unit becomes very small, it becomes unstable at room temperature. Because in fact, we talk about competition between energy of anisotropy versus room temperature fluctuations. So if the size becomes smaller, it becomes unstable at room. So one needs material with very high volume magnetic anisotropy. Another way is to go upward and to do 3-dimensional memory. For example, by making what you see here is just the magnetic film, which is in fact 2-level magnetic film. So one with perpendicular anisotropy and the second one with perpendicular anisotropy, and that's why we have in fact 2 layers or 2-bit one on top of the second. As long as we talk about hard disk memory, there is one problem. When the magnetization is parallel upward or downward, this is stable. But when we have anti-parallel magnetization of the bottom and upper layer, this state is unstable. So in order to make it stable, you should make larger spacers, so to make the film thicker. But then if you come from top with the head, you do not see the bottom layer. And that's why, despite that the idea is known, no one applies it in hard disk memory. Then you can go to magnetic random access memory. Magnetic random access memory means that each unit has its own address. So what people do today, and I'm sure that there will be a product within, well, some year, 2, 3 maybe, this random access memory is based on tunneling magnetoresistance. So tunneling magnetoresistance means that you make some kind of column, and here you need that this part will keep your magnetization constant, and you will be able to orient the second one. Here there are 2 problems. The problem number 1 is that the idea is to go to 20 nanometer size. And since what I have shown you probably before, I mean, the idea, oops, sorry, I go the wrong direction. In order to make these tunneling magnetoresistance, so giant magnetoresistance structures, in fact, they are enormously complicated. I mean, there are many layers of different materials. Okay? And if you make it 20 nanometer size, there is no knowledge how to etch, how to generate this column, very complicated column, and so small. This is one problem. The second problem, which is not less important, is that you need this insulating layer here, MgO. Now, this MgO is needed, first of all, in order to read the memory by tunneling. But the second one is when you want to write the memory, to orient the magnetization of one of the layers, what people once upon a time did, they did it with, let's say, magnetic field generated by electrical currents. But now the idea is that you can change the magnetization by pushing polarized current by spin transfer torque. That means that in order to write, you have to push here very strong currents in the range of 10^9, 10^8, well, ampere per centimeter square. That means that you generate high electrical field across this tunnel junction, and you kill it with time. Okay? So what we try to do is to make an entirely different approach to this problem, and just to use the extraordinary Hall effect. And the idea is, and moreover, and we try to build the, let's say, three-dimensional extraordinary magnetic random access memory based on extraordinary Hall effect. And the idea is very simple. Imagine that you have one magnetic dot and the second magnetic dot. This has both of them have perpendicular magnetic anisotropy, but with different, let's say, coercive field and magnitude of the phenomenon. Now you connect them electrically, and you measure voltage between this point and, say, this point. Then what you have Hall contribution from here, Hall contribution from here, and resistance transition from one to the second. The signal that you will measure will in fact include all these contributions. Okay? Now what we know to do, and this is due to symmetry of the anisotropic of the Hall effect, we can reduce all the symmetric part, so we can reduce the entire resistance, and we can stay with anti-symmetric part only. And then if we have that, then what we get the signal which would correspond either to both parallel up, down, this way, or this way. Okay? So the result would be like this. So this is the proof of concept of multi-bit EHE memory, when what you measure here, for example, this is the voltages, 4 states at zero field, which correspond to 2-bit memory. Now, if you would do the same game with, let's say, 4 layers, so you have 2 parallel, you have 4 storage dots, which means that you have 2 power 4, so you have 16 states. And this is the demonstration of the 16 states memory. The nice thing here is that what we do, in fact, we split the cell into different parts. These parts can be located in different positions at different floors of the structure. And we can get rid of all the electrical contribution, ohmic contribution between them, and measure the EHE contribution only. And the final thing that I would probably make, this is indeed the question that you started today, and this is merging of spintronics with semiconductors. Now, it's easy to when you have an introduction has already done, but you see, one of the things that basic problems of incorporation of, let's say, metallic ferromagnets with semiconductors is the transition between ferromagnet into the semiconductor, right? And that's why it is understood by everybody that what one needs is to generate ferromagnetic semiconductor in order to induce it and to use it. Now, how people do produce ferromagnetic semiconductor? You take semiconductor and you dope it with ferromagnetic impurities. And then ferromagnetic impurities contribute both the local magnetic moments and the charge carriers that will run all around and transfer information, right? The problem is that typically solubility of ferromagnetic impurities within semiconducting host is very low. And that means that if at the moment you put 1% of, let's say, for instance, manganese into, well, I know about germanium, I don't know about indium arsenic. What you get phase separation. You get clusters of ferromagnetic rich in magnetic contributor clusters and diluted matrix which is not magnetic at all. Okay? And that's why, in fact, I mean, one can argue when people see some kind of hysteresis response by measuring this type of material, does it mean that the material is indeed homogeneous and bulk ferromagnet? Or it means that you have ferromagnetic clusters sitting within the matrix, and these are the clusters that generate you the entire signal. But if we talk about, let's say, Hall effect as a way to implement spintronics, I don't care. I don't need ferromagnetic state, because it's sufficient for me to have ferromagnetic clusters embedded within conducting semiconducting matrix in order to generate spin-orbit scattering, which will be magnetically sensitive. And so, well, this is just some kind of example of that we measure EHE in the material, which is definitely not ferromagnetic, but is based of conducting semiconductor with localized ferromagnetic clusters, and we do have extraordinary Hall effect response. Well, that's it. Thank you.
Your clusters, what size do they have to be ferromagnetic, or?
Well, it's the question of temperature, right? I mean, this is super paramagnetic cluster. Depending on their size, we will get different blocking temperature, right? So if they are large enough, you can definitely get them, you can get, let's say, hysteresis at room temperature. So this is room temperature, well, maybe not room temperature, but this one is, well, I don't know, yeah, 300. So this is room temperature, but this is only the question of the size of the cluster, because the blocking temperature depends, let's say, you will take the volume, anisotropic energy of anisotropy multiplied by the volume, and that's what gives you the energy.
So you want to use these clusters then?
Yeah.
You want to use them?
Yeah.
Just a side, in our indium antimonide, we see 550K. T sub C.
That's fine. This is absolutely fine, because again, this magnetic, the clusters which are manganese rich, or depending on what you put inside, they can have a Curie temperature to very high temperatures. So the moment we're below the Curie temperature and below the blocking temperature of the cluster, you will get by this type of response. But it still doesn't mean that the material is a ferromagnet.
But the matrix still may be paramagnetic.
It can be, true.
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 Any other questions? If we have none, then let's thank Sasha again for